All right, welcome to The Explainer. Today, we are diving headfirst into the strange, wonderful, and let's be honest, totally mind-bending world of quantum physics.
You know, everything you see around you, everything your gut tells you is real, it follows a certain set of rules, right? A car is either parked or it's moving. It can't be both. But what if I told you that on the most fundamental level of reality, the rules are completely different? That a particle, the tiny little thing that makes up that car, can be both at rest and moving at the exact same time.
So what we've really got here is a tale of two worlds. There's the physics of our everyday lives, what we call classical physics. And it's great. It's perfect for describing, a baseball flying through the air or planets orbiting the sun. But the moment you zoom way in, down to the microscopic realm of atoms and particles, it just completely breaks down. The rules don't work anymore. And for that, we need a whole new rule book, quantum physics.
And that word quantum, it sounds intimidating, but it just comes from the Latin word for how much. It's really just talking about the smallest possible packet of anything. A little chunk of energy, a blip of matter, you name it. We're talking about the absolute bedrock of reality here. The electrons, the photons, the quarks, all the tiny little bits that build everything else.
Okay, so how do we know any of this weird stuff is true? Well, let's look at probably the most famous and maybe the most important experiment in all of quantum physics. It's called the double-slit experiment, and what's so brilliant about it is that it packs all of this incredible weirdness into one surprisingly simple setup. So here's the question I want you to think about. Imagine you've got this tiny little gun, right? And it can fire single electrons, just one by one. You aim it at a wall that has two skinny little slits cut into it. And behind that wall, there's a screen that lights up wherever an electron hits. So, what kind of pattern do you think you'd see on that screen?
Okay, common sense tells us these electrons are like tiny little bullets, right? So, each one's going to go through either the left slit or the right slit. And then thwack, it hits the screen behind it. After firing a bunch of them, you should just get two straight lines, two bands on the detector, one lined up behind each slit. Makes sense. Simple.
But that's not what happens, not even close. That common sense prediction is completely, totally wrong. Nature has a very different idea.
What you actually get is this stripy pattern with lots of bands. And this is the really weird part. This is the exact pattern you'd expect to see if you were sending waves through the slits, like ripples in a pond. The waves would go through both slits, interfere with each other, and create this pattern of peaks and valleys. But we're not firing waves. We're firing single individual particles.
And this is the part that just broke physicists' brains for decades. This interference pattern shows up even if you fire the electrons one at a time. So think about that. If there's only one electron flying through at any given moment, what is it interfering with? The only possible insane-sounding answer is that it's interfering with itself, which means it must have somehow gone through both slits at the exact same time. So to even begin to make sense of a result like that, we have to basically take our common sense rulebook, crumple it up, and toss it in the bin. We need to learn the secret rules that reality is actually playing by. Okay, secret rule number one is a doozy. It's called superposition, and what it means is that a quantum particle has this mind-bending ability to be in multiple states or multiple places at the exact same time. It's not here or there, it's kind of everywhere at once, existing in this weird fuzzy cloud of all possibilities. Physicist Brian Cox has a fantastic way to think about this. He talks about a quantum coin. Now, a regular coin, right? It's either heads or it's tails. Simple. But a quantum coin can be in a superposition. It can be, say, 30% heads and 70% tails, or any other mix you can imagine, all the same time.
So what this all means is that until we actually look at it, until we measure it, that little electron exists as a wave of possibilities. It's the very act of us observing it, putting a detector at one of the slits to see where it went, that forces that whole cloud of possibilities to just collapse into one single definite reality. Before we look, it's everywhere. The moment we look, it picks a spot.
And just when you think it can't get any weirder, it does. The legendary physicist Richard Feynman figured out that this doesn't just apply to our little two-slit experiment. A particle going from point A to point B doesn't just take one single path. No, It simultaneously explores every single possible path you can imagine, and I mean every path, including ridiculous ones that go all the way to the Andromeda Galaxy and back in an instant. All of these possibilities happen at once, and they interfere with each other to create the single path we end up seeing.
Okay, so individual particles are deeply, deeply strange. We get it. But believe it or not, the way they connect with each other can be even stranger. This leads us to one of the most famous concepts in all of physics, quantum entanglement. This is what happens when two or more particles get linked up in a very special way. They become, well, fundamentally connected. They're basically part of the same quantum thing, and what happens to one is instantly tied to the other, no matter how far apart they are.
So let's paint a picture. Imagine you have two of these entangled electrons. You keep one here on Earth, and you send its partner all the way out to Pluto, billions of miles away. The very instant you measure your electron here on Earth and see that its spin is up, you know instantly, faster than light could ever travel, that its twin on Pluto must be spin down. It's like they have a secret, instantaneous connection. Their fates are completely locked together.
Now, this instantaneous link, it really bothered Albert Einstein. I mean, he was the guy who said nothing can travel faster than light. He famously called this spooky action at a distance because he just couldn't accept it. It seemed to break his own rules. But here's the thing, experiment after experiment has proven that this spooky connection is absolutely real.
Okay, so superposition, entanglement, this is all pretty mind-blowing stuff, right? But you might be wondering, is this just some philosophical curiosity? Is it just weird for the sake of being weird? And the answer is a resounding no. This weirdness is actually being wired directly into our world, right now.
See, these bizarre quantum rules aren't just for textbooks anymore. They are the actual engine driving a whole new generation of technology. And the most famous example of this is the quantum computer. So think about it this way. A normal computer bit is either a 0 or a 1. It's like a light switch, on or off. But a quantum bit, or a qubit, thanks to our friend's superposition, can be a 0 and a 1 at the exact same time. It's like a dimmer switch, and this one little change means its power just explodes exponentially. 2 qubits can hold 4 values at once, 3 can hold 8, 4 holds 16. You see where this is going. Okay, so let's really scale that up. What if you had a quantum computer with, say, 500 qubits? Well, the number of states it could handle at the same time would be 2 to the power of 500.
Now, I want you to try and wrap your head around that number, 2 to the power of 500. It's a number so ridiculously, astronomically huge that it is larger than the total number of atoms in the entire observable universe. And all of that incredible computational power could, in theory, be packed into a machine that fits in a single room. That is the power that quantum mechanics unlocks.
You know, this idea that the observer actually shapes reality, it feels very modern, but it's not. There's this ancient Sanskrit verse that says, "As the vision, so is the creation." And it really makes you think, doesn't it? We've learned that a particle is just a wave of pure possibility until we decide to look at it, which leaves us with a really profound final thought to chew on. What role does our own observation, our own consciousness, play in creating the universe we see around us?